Hello everybody. In this video, let's focus on the evaluation of performance of TCP and another variant of TCP, that is Neureno and Vegas. So we'll be just looking at the standard TCP and then the other variants, Neureno and Vegas. These three variants we'll be looking at. So to start off with, what we'll do is we'll just focus on the TCP part. We'll understand this and then compare it with the other variants. So we have the network topology here. What we have is at a high level, we have a LAN over here, and then we have another LAN over here, and these two LANs, they are connected by a link over here. This is the WAN link. And what we have done is we have made this WAN link to be relatively of lesser bandwidth when compared to the, or lesser data rate when compared to the data rates in the LAN. And we have kept a source over here. So we can see that there is a FTP here which uses a TCP, and this source and the destination is to the other side. So we can see the sink over here. So we have this node 4 as the destination. So this TCP, or rather this FTP, through the TCP, it will send the data to this destination on this LAN. And definitely all the traffic should go through the weak link, that is the WAN. So now we know that the TCP, it's a reliable protocol. The TCP here, or the transport layer TCP protocol here at the source and the TCP at the destination, these two work together to make sure that whatever packet is being given from the FTP is delivered to the other side. So by way of, we know, by way of acknowledgements, and then it should also make sure that they are all in order. Whenever it is given to the application layer here, they should be in order. Whatever has been transmitted here, the same order will have to be maintained here and given. And the other thing to note is TCP exists only at the source and the destination. There is no TCP or the transport layer in the intermediate nodes. And that's the reason TCP doesn't know what is there inside, how many hops are there, or it doesn't have any clue of how the packets are going to the other side. That is what we need to remember. So only view that this TCP will have of the network is the data that it, or the information that it will be getting back from the acknowledgements. Whatever is being transmitted from here, and we know that the acknowledgement will come back. So from the round trip delay, how much time it is taking to go to the other side and for it to come back. So it gets an idea of, the TCP gets an idea of what is the congestion like. Is there a congestion, or basically can it send more data, more rate, and those decisions the TCP will be making. So in this practicals, what we'll focus on that property of TCP which will adopt, it will try to adopt to the link, because one thing is it would want to make use of all the data rate that is available, so that it can get its packet as quickly as possible to the destination. That is one thing. So it would want to, if traffic is less, it would want to kind of increase its traffic and send those packets across. On the contrary, if it notices that there is a congestion, that is by way of acknowledgements that are coming back, if acknowledgements are dropped or acknowledgements are taking too much time to come back, so it realizes that there is some problem between him and the destination. So that means there is a congestion. So in that scenario, again, he would want to slow down, because he would not want to add to the congestion. He would want to slow down, that is slow down his traffic, so that in case he doesn't slow down, his packets will be lost. Again, he'll have to do retransmission. He is in fact adding to his work. That's the reason he would want to avoid the congestion. In case congestion is happening, he would want to avoid. And on the contrary, if the congestion is not there or acknowledgements are coming back, then he would want to kind of increase the traffic, his traffic generation, so that he can get those data as quickly as possible to the sink. So points to remember, TCP does one thing, it tries to adopt to the available data rate in the channel, so that it can make use of the channel as best as possible. Second thing, in case there is a congestion, it would want to slow down. And how does TCP do that? TCP does that by adjusting its window of pipelining. Basically, all of us know that TCP will be sending a window of packets even before the acknowledgements are coming. So you would want to send, say, some 8 of them. So even before, he's just sending them across before the acknowledgement comes, and he'll just wait for those acknowledgements to come. Once the one of the acknowledgement comes, then he'll send the 9th packet. So that way, he's just making sure that only 8 packets are there on the channel which are not acknowledged, not more than 8. That's just example. So that window, he would want to adjust it based on the congestion view that he is having. So if it is link is congested, then he would want to make that 8 to say 6, 4 or 2, or at the minimum he will make it as 1, where it will start working as a stop and wait. Or if he doesn't see any congestion, he sees the link to be good, he would want to kind of increase that window size to say from 8 to 10 to 14, so that he can keep sending more packets. Let the acknowledgement come, even if the acknowledgements are taking some time to come, he'll keep pipelining all those packets. That's how TCP handles. That's the background that we know. Now let's focus on how the standard TCP handles the congestion window, his congestion windows. Likewise, later in the later videos, we'll see the new Reno and Vegas also. So let's quickly jump into the practicals and let's build this network scenario. So I'm just opening let's minimize this first. Let me move it to one side. Yeah, we have the Ubuntu here. So let's maximize this now. Yeah, and then as before, let's start Java -jar nsg or network scenario generator should come up. Yes, it has come up. And then we go to scenario, wired scenario. We have 2 nodes here and a router for this LAN, and then another router for the other LAN. So we have 2 nodes here, and we know, let's get to the link and link the first LAN. It had said 1 Mbps, and I think it had said 10 millisecond itself. Just to confirm, let's have a look at it. Yeah, it is saying 1 millisecond, 10 millisecond and 50. Okay, we are on track. So we'll just put the link. Just remember, we should always put the link from source to destination. So we are planning to put the source here. So we'll put the link like this, and from here to here. So in case we put a source here, right now in this experiment we are not putting it, but anyway, fine. And then on the other LAN, we want to have a link of 0.5 Mbps rate, and delay of 50, queue size of 10. Okay, let's do that. On the other side, we want to put it as 0.5, delay of 50, and queue size as 10. Okay, let's reduce the queue size to 10. And remember, again, from source to destination, in the sense like the flow of packets, source to destination. And then we want to make the WAN link to be weaker. So we are making it 0.1 Mbps only. And then we are making it 0.1. We are increasing the delay by 100 milliseconds, and the queue size we would want to retain it as 10. Okay, fine. So remember, most of the students do a mistake that they put this link from N3 to N2. So it should rather be from the source. Packets will travel from here to here. So the link should be this way. And then let's go to the agent, and we want to put a TCP agent, and the demo had said packet should be of 2048. Okay, let's put the packets as 2048. And then this is the TCP. And remember, there are lots of variants of TCP here, New Reno and Vegas. So as of now, we are using the standard TCP. So later experiments will be using the other variants, New Reno and Vegas. Fine. Then we want the sink here. We'll put the sink here, and this TCP and this TCP should be connected. Finally, we'll go to the application. Application, we want to run it for a long time. Let's say we want to run it for 125 seconds. And okay, once we have the TCP, we should add the FTP now. So we have the FTP starting here. we have added the FTP, and then we get to parameters. In the parameters, we want to set the simulation time. We have set it, everything is fine, and we name the files. We go here to the TCL, and then we will save this. We'll save this as, we'll get into our work area. We'll save it as experiment 07-tcp.tcl. So we save this. We'll go back to the terminal, and so we opened it. So we'll just scroll up, and yeah, we'll start off with the color code that we want to set. Color 1 red. And then we want to define a congestion window file. So just we are just using we are opening a file in the same format as the SNAM or trace file. So we'll just go open experiment 07 TCP, and remember, we'll have to end this file with -cwnd.dat and open it in write mode. Okay, and then we go down, scroll down, and the links. Remember, we want to observe the WAN link, the queue in the WAN link. So let's have a look at the WAN link, which is the WAN link. Yeah, let's close this. This is the WAN link that we want to observe. We want to observe the queue here, that is between N2 and N3. This is what we want to observe in NAM. So that's the reason we'll come here. We'll say NS duplex link $N2 $N3 QUE UE position as 0.5. Okay, that's filling the NAM. And then we want to see the packets as red in color. So that's the reason we are saying we're setting the flow ID to 1. And then application is fine. And okay, before that, in the agent, we also want to see or record the congestion window sizes that TCP0 will use, or the TCP agent, that this is the standard agent that this will use. We want to record it. That's the reason we have a function in the manual here. Okay, that's highlighted already. Let's copy it. Let's go back and let's paste it here. We'll have to be okay. We got it something wrong. We'll do a Control Z. We'll go back here. Oh, okay. Only a part of it was copied. So we'll highlight the whole thing, copy it, come back, Control V. So everything is intact. Let's have a look. Everything is intact. So while copying, you'll have to be very careful. So you might miss some parts, or it might get jumbled up, and those things you'll have to be careful. And in the finish function, we want to close the file that we had opened. This is the handle, which is global, and then we want to close it. Close $CWND file. This is what we need to remember. Very careful. So this, in fact, these instructions are there in the manual also. So these are the things that we did, closing the file. Okay. So let's save this. Let's get back to the terminal. If everything is fine, NS experiment 07 tcp.tcl. Okay, if everything fine, it should compile peacefully. Yeah, good, it compiled. So no errors. So let's see if the animation is what as per our expectations. Let's keep it like this. Let's start it, and then we can see the time is ticking. Okay, and let's slow it down, and we can see that the TCP is sending and the queue is building up over here. Let's see how TCP adjusts to it. So let's increase it a little bit. Okay, now we can see the queue is slightly growing. Yeah, we can see there is a packet drop. When the packet drop, the TCP didn't receive one of the acknowledgement. Let's see what TCP does. Yeah, you can see that it has slowed down the traffic that is generating. From the queue that you can make out, queue fell down to 0. Now it realized that in fact there were some instances where the link was not being used, and it realized that the link can be is not being effectively used. So it started sending in more traffic. Now again you can see that from the queue we can see that the TCP's or the traffic generation by the TCP source is increasing slowly. So slowly it is increasing. Again it will touch 10. We had set a limit of 10. So that's where the packet will, when the packet will drop, again we can see that TCP will again hold back. It will try to avoid the congestion. Yeah, we can see there was a packet drop, and TCP is now slowly, yeah, it is slowly kind of reduces traffic. Now we can see there are instances where link was free. That is how it is oscillating. Anyway, so let's stop this and let's see what is happening to the congestion window. So in fact we had saved, we wanted the data saved in, we'll do a gedit of it, experiment 07 dot tcp cwnd dot data. This is the file that we wanted the congestion window to be saved. Yes, it has nicely saved it. Now we can see that this column is all timestamps 01, 02, 03. Every 0.1 seconds it has recorded what is the congestion window being used. Congestion window of 1 was being used. Slowly the congestion became 2. Congestion window became 3, 4 and all those things. So it is pipelining more and more packets. Okay. So from this data, the best way will be to kind of plot this and see. Let's plot it now. So let's close this. Let's get back to the terminal. To plot it, first thing is let's remove first. If there are lots of data files. First, let's remove. Let's remove all the data files, and then let's again run the simulator. As of now, we are not interested in this, looking at the animation. So we'll have the data file now. If you see ls start.dat file, we can see that there is this file that the simulator has generated. To see the plot of it, we do a GNU plot, and we use the script mgit underscore cwnd plot.p. We hit enter, and then we have the graphs, Naives graph, which depicts what is happening to the congestion window. Let's this is the x-axis, that is the time axis, and this is the window size that the TCP is using. So let's not worry about this. Now we can see that this now the congestion window TCP basically it started off. If you observe, this is the 1. It started off with 1, that is stop and wait protocol, and slowly it realized that the acknowledgements are coming back. It is trying to adopt to the link now. It is trying to pipeline more and more packets. It is pipelining 6 packets, it is pipelining 8 packets, still the acknowledgements are coming back. It is trying to pipeline 10 packets. Slowly it's trying to, it's increasing the window sizes, 12, 14, it pipelined 14 packets, and realized when it reached 14, it realized that there was a packet drop. One of the acknowledgements didn't come back. And since it didn't come back, it immediately realized that there is a congestion in the network. And so what it did was, it stopped pipelining. Immediately from 14, it immediately dropped the pipelining or the window size to just 1. It said, okay, now I am not going to send the packets. I'm just going to send 1 at a time. Only after I get the acknowledgement back, I'll send the next one. That is what it is saying when it says window size is 1 or stop and wait. And it did stop and wait for a certain time, and then it realized, okay, let me adopt to the link. Since the acknowledgements are coming back now, let me adopt to the rate of the link. So it now started pipelining 2 of them, then 4 of them, 6 of them, and the cycle repeats again. It slowly, gradually adopted. It increased the window sizes. It went till 14. Again, there is a packet drop, and that's where again it is adjusting it, and it's going back to stop and wait. So it is oscillating between say a maximum pipelining versus stop and wait, where there is no pipelining at all. So we can say it is oscillating continuously. And we know pipelining gives us efficient mechanisms because the link will be utilized completely, whereas stop and wait is inefficient. So that means the traffic or the traffic generation by the TCP, it is oscillating between sending efficient transmission versus inefficient transmission. That is how it is oscillating. The standard TCP is oscillating. Okay. So this is how the standard TCP is working. So to look at now New Reno, what we'll have to do is New Reno or Vegas. We'll again have to plot their congestion window, how they are handling the congestion window, and then compare them. So is it the same way or are they doing it in a different way? Anyway, so we'll do that in the next video. So before that, so let's also look at the throughput of what is the throughput that is obtained. So for looking at the throughput, we will have to look at the trace file. I mean, analyze the trace file. To analyze the trace file, we have MGAT wired. We'll use the 5th version. In fact, wired underscore. Yeah, we'll use 5th version. awk and the trace file 07 -tcp dot trace file. We'll use the trace file. Yeah, this is the output that we have got, and we can see, okay, there are these acknowledgements. We are not worried about the acknowledgements. Let's have a look at the TCP. So let's look at TCP and frame sizes. Now it is saying that it is using this traffic basically between 0 to 4. It has two types of frames, one of size 40, another size of 2088. So if you see, we had set it as 2048 in the application. Now you can see 40 additional bytes have been added to the packets that have been sent. Those 40 bytes are nothing but 20 bytes of TCP header and 20 bytes of IP header that had been added to it. That's the reason we see a big number over here. Start time, end time, and it sent 708 packets. And look at the delivery. All of them have been delivered. 708 of them have been delivered. Though there were some drops in the middle because of congestion. We can see the reason being congestion. And it retransmitted them because TCP is reliable. He detected that they were dropped. He retransmitted, but he probably retransmitted a little bit more than what were actually dropped. That is, 12 of them are duplicate. The receiver detected that they are duplicate. Anyway, he has got all the 708 and the delivery is 100%, which indicates one, that TCP is reliable. Whatever has been given to him, he sent it. That is one thing. The second thing to note is just observe the throughput that he has got, the raw throughput that he has got. In fact, the WAN link, if you observe, it was 0.1 Mbps, which is nothing but 100 kbps. Now observe this TCP or the standard TCP, he was able to achieve 95 kbps out of 100. He was able to utilize 95 kbps out of it. The reason for a small drop here from 100 to 95 is because sometimes the TCP had left the link to be free. It was not utilizing it because it had dropped down to the stop and wait mechanism. So those are the insights that we get from this statistics. Good. So next thing is, let's plot this throughput. To plot it, what do? Is we do a GNU plot. We use MGAT underscore throughput plot, and then we run this. And this throughput plot, the script that is there, MGAT throughput plot.p, it in fact searches the directory for all the files that have extension of -th.dat. So in fact, our awk file had generated these two files. One is for the traffic related to acknowledgements, other is traffic related to TCP. And GNU plot, this particular GNU plot script looked for those files that are listed here. It found that there are two files and it plotted them. And this is for acknowledgement, and this is for the TCP throughput. We are not interested in acknowledgement, let's leave it off. Whereas this is the actual throughput that it achieved. So over a period of time, and this is the throughput in kbps, we can see that on the average, the standard TCP obtained, though the data rate or the capacity of the link was 100 kbps, it was able to reach till 95 kbps. Okay, these are the learnings that we have from this practical. So in the next video, what we'll do is we'll continue on this and we'll look at how the neuron performs. So see you in the next video.